Why? Because our energy is no longer confined in the bonds of a molecule, okay? It's been released, and now the microstates where it can be dispersed are a lot more than they were when they were confined in the bonds of the molecule. Okay. Whoops. Okay. So, exothermic reactions involve a release of stored chemical potential energy to the surroundings. And so that's why exothermic reactions tend to favor spontaneous processes. Because what does an exothermic reaction do? It disperses energy, right? Exothermic reactions disperse energy. This says the stored potential energy starts out in a few molecules, but is finally dispersed over a great many molecules, right? So if we have a reaction that takes place, we have stored potential energy that starts out confined in the bonds, but it is dispersed over a greater number of molecules. The final state with energy dispersed is more probable and makes a reaction spontaneous. Okay? Okay. And so again, here's our picture. The entropy of gases is greater than the entropy of liquids, is greater than the entropy of solids. So if I were to write up here on the board, solid water, and I heated it and I got liquid water, does this represent an increase in entropy or a decrease? This is an increase. However, if I had H2O gas and I cooled it down to water that was a solid, this would be what? A decrease. Okay? So again, as we go from reactants to products, we can have a decrease in entropy. If you look in a chart, all standard entropies of formation are positive. Okay? All right. And there's the actual comparison. And our entropy is in joules per Kelvin per mole. Remember that I didn't put that as the unit, but if you recall, we do multiply by the moles that are the coefficients in the balanced chemical reaction. Again, here's just an example. The entropy of bromine in the liquid state will be less than the standard entropy of bromine in the gas. Here, even in a liquid, even if they can kind of move past each other, their energy is still not as dispersed as it would be for bromine particles in the gas phase. Over here we have that we've already mentioned this one, water as a solid has an entropy that's less than water in the liquid phase. If you have water that's in the solid phase, it's constrained to an actual hexagonal structure. Okay, so there's fewer microstates for the energy to be dispersed, which is not true when you have liquid water. Those particles can slide around each other. All right, so now we're going to talk about entropy of a substance increases with temperature. Increases in molecular complexity generally leads to an increase in S. So here we have a series. Here we have methane, then we have ethane, and then we have propane. By having more atoms, we have more microstates for the energy to be dispersed in, which leads to an increase in S. what we're going to be talking about now, what we're doing right now, we're talking about specific indicators that would allow you to look at specific chemical reactions and decide whether our entropy is increasing or decreasing. All right, we know that our entropies of ionic solids depend on Coulombic attractions. That sounds like a real mouthful. All that means is that the cation has a positive and the anion has a negative, right? We call those Coulombic attractions. Now here, when we have magnesium 2 plus and oxygen 2 negative, those are fairly strong charges. Those are fairly strongly attached to each other. There's fewer places. The higher the charges are, the less energy dispersal there is. Here we have sodium and fluoride. The compound sodium fluoride has a higher entropy, okay? So that's kind of an inverse relationship. The lower the Coulombic attractions, and here we're just looking at the charges, okay? So if you ever take a physics or a physical chemistry class, you can actually calculate charges. We don't have to do that. This is just 2 plus and 2 negative. Higher charges. These are just 1 plus, 1 negative, lower charges, okay? So the lower those Coulombic attractions, meaning just the overall absolute value of the charges, the higher the entropy. So if you're comparing ionic compounds, that's how you do it. Alrighty? Yes?
So that magnesium oxide,
I'm saying it's lower.
that's low.
That's what I said. The higher the Coulombic charges, the lower the entropy. If I said anything else, then I am really, really, really sorry. You can hook me to my car and drag me across the parking lot or something. Yes?
Is that because they're attracted to each other more, so it's less likely that they're going to split apart?
Yes. Yep. Or interact with their neighbors, or interact with anything else in the neighboring surrounding. Okay?